Okay, thank you to the organizers for inviting me to speak. As everyone has said, it's been a really great workshop for the last week. So I'm going to talk about extremely optimistic things, because I'm an extreme optimist. So I'm going to talk about exploring ultra-large scale structure. So let's start by talking about what do I mean by ultra-large scale structure. So here is the observable universe. And here is ultra-large scale structure. So in general, I'm interested in scales that are about as big or a little bit bigger than the observable universe. Of course, if it's too big, then you can't see it. So why do we care about ultra-large scale structure from the theory side? Well, there's inflationary statistics. So, for example, local type primordial non-Gaussianity has to do with the coupling between very big scales and small scales. Of course, if you have a bigger lever arm, you can understand tilt and running of the power spectrum. You just get to see more U-folds of inflation. Perhaps there are funny features that we'd like to understand more about that manifest themselves mostly on large scales, small l in the CMB. And then there's a whole host of very fundamental questions that we really don't have much experimental data about. Multiverse. GR on large scales. Do we trust GR on large scales? Topology, isotropy, huge voids, curvature. All of these things are sort of data limited by the fact that we don't have too many modes on these large scales. So currently our best probe is the primary CMB. And from the data side, there might be interesting things in there. There are hints that funny things are going on. You know, lack of correlations on large scales, aligned multipoles, weird spots, power asymmetries, features, and so on and so forth. But sadly, sad CMB, we're just done. Like modulo understanding systematics and foregrounds and so on and so forth at low L in the polarization, there's really not much information that we can harvest left in the primary CMB.
I thought you said you're optimistic.
Oh, no, I have to set you up first. No, don't steal my punchline, Ichiro. Don't steal my punchline. Come on, you're going to see a happy CMB in one slide. Okay, so modulo this, the pessimists would say, oh, we're done. Okay, and then, you know, of course, I'm also going to be talking about things you might need Tylenol for, as we discovered from the poll last week. I know at least 25% of you get a headache by thinking about the multiverse, but maybe I'll give you a reason to not take the Tylenol. Okay, so here's your happy CMB, Ichiro. The optimist can say, well, actually, there is this amazing opportunity. As we heard from Lyman, there's amazing opportunity for measuring the high L CMB, and this is something we're getting extraordinarily good at. And you can learn information about large scales by thinking about the small scale CMB. So that's one thing I'm going to talk about. You already know one thing, which is lensing, right? That's an extraordinary opportunity to learn about large scales from small scales in the CMB. And then I'm also, if I have time, but probably I won't, going to talk about plenty of potentially observable things. So that's why you can ditch the Tylenol, because you don't have to break your head on the measure issue. Things to understand about ultra-large scale structure from the theory front. Okay, so here's a rough outline of my talk. On the data side or observation side, I'm going to talk about two techniques in CMB temperature and polarization at high L that might teach us about large scales. And then on the theory side, I'll mention two ideas very briefly. So let's start with data. The kinetic Sunyaev-Seldovich effect is a temperature anisotropy that's induced by the scattering of CMB photons from free electrons during and after the reionization era. In some sense, you can think of the KSE effect as providing a census of the locally observed CMB dipole at everywhere there's a free electron to scatter off of. And in some sense, which we can make more precise, we can in principle learn information beyond what we get from the CMB, because CMB photons can scatter from the bulk inside our light cone onto it. So in principle, there is information there to harvest beyond what we get from the CMB. So here's some equations. Here's the temperature anisotropies induced by the KSZ effect. You don't really understand much, but let's just note that in the presence of an inhomogeneous distribution of electrons, there's a term that goes like the density field times this locally observed CMB dipole. Usually we don't care about all the different pieces that go in there, because as we know from our CMB dipole, it's totally swamped by really small scale peculiar velocities. But let's care for a minute about that. So just note that in this equation, we have this sum over 3 moments projected onto the line of sight. And as we take the redshift to 0, this is just literally our observed CMB dipole. Okay, there's tons of subtleties with the dipole. I'd love to talk to you about them, but I don't have time. Okay, so the other thing is the polarized set effect. So if we look at the polarization of these photons that are scattered off of free electrons after reionization, in the presence of a quadrupole, you get a polarization in the presence of a quadrupole. And so the polarization anisotropies give us, in a sense, a census of the locally observed CMB quadrupole at the position of all these electrons. So every electron is a really primitive CMB satellite that tells us its dipole and its quadrupole in principle projected along the line of sight. So again, in equations, details don't matter too much, but I'd just like you to remember that in the presence of an inhomogeneous distribution of electrons, we have delta times the quadrupole field. So again, if we ask what does this do at low redshift, you'll find that as the redshift goes to 0, these things here are literally the locally observed CMB quadrupole, what we see when we make a map. Okay, so let me explain these ideas for getting large scales out now. So we can do tomography, by which I mean we want to know this bulk information about these large scale fields, the dipole field and the quadrupole field. We've got a backlight, the CMB. We've got large scale structure where there's electrons. They can bounce off of that large scale structure and come to us, inducing temperature and polarization anisotropies. And if we like, we can make some bins to think about this three-dimensional information in a sort of discrete way. And here's the equations. Okay, so we'll start with this KSZ piece, the temperature anisotropies. So we can imagine binning, taking the average over the bin of these projected moments of the dipole field. So then we can directly cross-correlate with a bin density field. There will be a Gaussian piece, and then there will be a non-Gaussian piece. Because as I told you to please remember, the KSZ effect due to the inhomogeneous distribution of electrons and the anisotropic dipole field is quadratic. Right? It's delta times this velocity field. So in spirit, we get delta delta V. And so because this average dipole field, thing I call V bar, is mostly going to change on really large scales, then this is like a squeezed limit. I mean, it's a local type non-Gaussian. So you should really think of it as a power asymmetry that's varying on the sky. And then there's some statistically isotropic piece that we're not going to care about. And the important part is that all the small scale contributions to the binned average CMB dipole cancel off because the small scale stuff is just as likely to be going this way as it is coming towards me. Okay, so in many applications of KSZ, that's what you want. That's your signal, so you square things. But I don't want that. I want to throw away all the small scale stuff. And this can, in principle, be an excellent probe of large scales. A lot of these ideas were pioneered by Pengji Zhang and Stebbins 7-ish years ago, and then we picked this up to explore it in a little bit more detail. Okay, so The subtleties about the dipole I'm going to fold into my definition of this binned average velocity, and I'm just going to call that the primordial dipole, meaning the part of the dipole that's sourced mostly by linear scales. So again, here's the signal, and just as a list of the jobs that tomography is doing for us, we want to boost the signal, we want to isolate this long wavelength component, we want to break up the line of sight integral to get three-dimensional information. And the signal in pictures is a power asymmetry. So I guess that's the part you should remember. Now there's the important piece. Can we actually detect this? And so here, as the ultimate optimist, we're going to assume something really optimistic, which is no foregrounds, full sky, cosmic limited, variance limited measurements of the temperature out to an L of 3000, and the angular matter power spectrum out to an L of 3000, and equally spaced redshift bins out to redshift of 6. Okay. So throw away the last two redshift bins, because those are probably way too optimistic, even for an optimist. But anyway, here's what you get. This is the per mode signal to noise that you could expect if you could do this, and it's huge, of order 10, per mode for the LMs. So there's a huge signal, and you can bin it up pretty finely and still be left with a pretty huge signal. So the first thing you could probably do is measure that first mode if you really could go to the full sky. And if you could do that, you'd learn something really interesting, which is a huge sigma detection of what we call our local primordial dipole. That's literally just go to the first redshift bin, the easiest thing to measure, a highest signal to noise thing. That's our local primordial dipole. So please, someone go and do this. Okay, so the other idea, this PSZ tomography, which we've already heard a little bit about from Ben earlier in the week. I know many other people in this room are doing interesting work on this, including Dan and Alex and others, perhaps. So this is the idea that we could extract information about this quadrupole by doing tomography. And of course, this is also a really old idea pointed out by Kamiankowski and Loeb back in '97. And again, we play the same trick. Take our anisotropies and polarization at high L, cross-correlate them with the density field. This is a three-point function. It's a local type non-Gaussianity. And so we can pull out information about this quadrupole field. Note that we modulate both E mode and B mode small scale power. That's really important. This is for exactly the same reason that you modulate both E mode and B mode power if you have patchy tau or patchy screening. Okay, furthermore, you can decompose this quadrupole field into E and B modes, which is useful because that's a way to help you separate the scalar contribution to the local CMB quadrupole from the tensor contribution. So in principle, this is a way of getting at tensors as well. Okay, but first the scalar piece. So again, with the same equally optimistic assumptions, except for now for polarizations, they're more optimistic, but I'm an optimistic person, and you convince me I should be an optimistic person, because we will invent something to allow us to do this in the near future, undoubtedly. Again, you can get at a high mode-by-mode signal-to-noise in principle. And I think this is not too crazy, and it roughly agrees with what I understand various forecasts that are done a little bit more realistically will get at. So what's the first thing you can measure? Again, go to the first bin and measure what we think should be our local CMB quadrupole. But what if it's not? It doesn't have to be. The only reason it has to be very correlated with our local CMB quadrupole is if we assume the universe is statistically homogeneous on really large scales, but it might not be. So that's a really interesting first test of statistical homogeneity on very, very large scales that can in principle be done, maybe even in the very near future. So as I said, you could use this technique to also get at B modes. This is something that was first pointed out by Alzadeh and Harada. So they forecast you might get down to an R of 0.1 or 0.01 with this method. And I think roughly speaking, what we've done agrees with that. So you could imagine reconstructing the actual map of gravitational waves on large scales in the universe using this method, three-dimensional map. And your reconstruction, mode by mode, with these same assumptions that I've made before, is going to be order 1 per mode for singleton noise, for an R of 0.1. Okay, so what's next? I think these are becoming realistic, at least for what we envision for the future of the CMB. So theorists, please start thinking about interesting things to do with this. Observers, please start thinking about how to measure it. And it'd be really interesting. I mean, this would be a new window on ultra-large scales that it's really hard to get at in basically any other affordable way. Okay, so to the extent that I have any time left, how much time do I have left, Shirley? Done. Okay, then I'm done. You can ask me about the theory slide later. Thank you so much.